you guys want to learn something more practical that you can apply in everyday programming, multi-threading is as practical as it gets, I think. So we will try to build a simple thread pool today, building on everything we've learned so far. So let's first start with some components that we're going to need. We will certainly need a thread, and more than one. Otherwise, it wouldn't be a very good thread pool. So I'm going to be using STL thread. And just mention real quick here. There we go. You know, everything I'm building and teaching, I'm always striving to use only standard components. So what I built here today on the Mac, you should be able to take that code, compile it on Linux, and compile it on Windows. The only thing you may need to do is adjust the language settings accordingly, since I often mix things that were introduced in C++ 11 with things from C++ 14, and then I know some things from C++ 17. Sometimes I'll throw in a concept here and there, so that's even touching on C++ 20. And I don't particularly care to remember which language standard the given feature came from. So my suggestion is, for compiling these sample programs, either switch your compiler to at least C++ 17, or if it supports newer than that, switch it to the very latest and greatest. On Visual Studio, I know you can set it to latest draft. There's C++ 14, 17, and then latest draft. And then on LLVM, on the Mac here that I'm using, it already has a std C++ 20 option, since then we already have the 20 standard. Okay, we're going to need a thread. We're going to need mutex, probably because there will be some locking involved, right, in a thread pool, since there will probably be a shared data structure somewhere, maybe like a queue of tasks to do. Let's see what else. Speaking of queues, we will probably need a queue. And I already mentioned this, but we will need a condition variable. Okay, but before we dive into the nitty-gritty detail of building a thread pool, I wanted to have mentioned something about a condition variable. And let's see, let me bring up the doc for it, so because it's listed here. So let's imagine that we are building this thread pool. We have a pool of threads that are sitting there waiting on some work to do. And then a consumer of this thread pool comes around and issues queues a work item. Says, hey, thread pool, here's something I want you to do on the thread pool. So the thread pool would likely lock a data structure like a queue, push it onto this queue, and then unlock the queue and notify one of the threads that some new work item is ready to be processed. So that would involve an event and a mutex. Or it could. One of the designs could, and it wouldn't be a good design, but it's easy to make that mistake. So what could then happen is a thread receives an event. So then next thing it tries to do is it tries to lock the mutex. But it is possible that in between the time of the event being signaled and the thread being able to lock that mutex, and on another thread, a consumer pushed another work item onto the pool. So that resulted in, again, locking the data structure and issuing the event again. So that could wake up another thread that would receive the event. And it is possible that this other thread in the thread pool could lock the data structure first. And then you could deal with it, but it would get kind of messy, having to do these checks and, okay, there was an event, I got the lock, but is there actually still something on the queue for me to do? So condition variable sort of not sort of. It solves this problem. I like to think of it, maybe it's right, maybe it's wrong, but I like to think of it as a marriage of a event and a mutex. Because in order to work with a condition variable, you actually do need a mutex. But what a condition variable allows you to do is it allows you to fire an event, so notify, and at the same time acquire a lock on said mutex. And it does it atomically. At least from your point of view, it does it atomically. So it's all or nothing, right? When you wake up from a condition variable wait because of somebody else signaling it, then at that point you already have the mutex locked. So there is no possibility that somebody else will wake up and get in your way and step in between you waking up from an event and locking a mutex. And it's described here on the cppreference.com site, this is my go-to place, by the way. If ever I need look anything up about a standard component, I just go right here. So it says that any thread that intends to wait on a condition variable has to acquire a mutex, which is the mutex used to protect shared variable. Check the condition, and I'll explain later what that means. Execute a wait, and the wait operation atomically releases the mutex and suspends the execution of the thread. And then when condition variable is notified, or a timeout expires, or a spurious wake up, and we'll get into that as well, the thread is awakened and the mutex is atomically reacquired, right? So two things happen. You are woken up and you have the mutex. And this will be critical in getting the thread pool working correctly. Spurious wake up, I'll mention this quickly, is when the thread is woken up, but not because the condition variable has been notified. It may be for some other reason. A signal or operating system maybe wanted to wake up the thread to do some work on it. So condition variable allows you to check for that and see whether you've been awakened because of said spurious wake up or because somebody else actually notified you that some condition has been met and you are ready to proceed with your work. Okay, let's start by designing a simple interface of the thread pool and start writing a little program that starts using it. So class thread pool public private and let's here in the main write the actual client code. So thread pool, let's call it TP, and that's it for now. So thread pool is certainly, you could say, a resource owning object. So we will make it non-copyable, non-movable. You create an instance of it, and that is the instance you are dealing with. So thread pool, const thread pool reference, so copy constructor, delete, and we'll do the same thing with assignment operator. Operator equals const thread pool. So this is us stating our intent explicitly that we do not want this thread pool to be copyable. And by just marking those two deleted, that already, I believe, wipes away the move constructor and move assignment operator. So there's no need to mark them deleted. But for completeness, let's do it. Because I am honestly not 100% sure if they would, I'm pretty sure they would be deleted or simply not defined, which there's apparently a difference. Whether a constructor or a special member is deleted explicitly or not defined. If it is deleted, I think it can still take part in name lookup. kind of like a function lookup when objects are created and moved or copied. And you get one error stating that you're trying to use an explicitly deleted member function versus if it's not declared deleted, it just doesn't exist, the compiler wouldn't even attempt to look for it. I think that's the difference. But again, don't quote me. And move assignment operator. Okay, we delete
Martin,
those.
have you ever used ReSharper?
Have I used ReSharper? Yes, briefly on my development box at work in Visual Studio. But no, I don't really have much experience with it.
ReSharper sometimes gives you messages about the code and whether things, special member functions are deleted or defaulted. It's pretty helpful.
Okay. Yeah, I actually have in my development toolbox, I have C Lion from JetBrains. That's their IDE for C++ and C#. And they were kind enough to give me a free license, well, which now expired. But I haven't used it in over a year. But they have a program, you know, for bloggers and open source contributors. So I contacted them and said, hey, I have this blog, and you know, I contribute to the community and write these articles, and I publish them for free, including the source code. And they're like, okay, oh, that's great. Well, here's a license for the complete tool set. So yeah, this JetBrains toolbox, and it allowed me to install C Lion. And I know that C Lion came with ReSharper, but I'm so used to Xcode that I'm just using that here on the Mac. Maybe I'll need to contact them and see if they would be kind enough to issue me another license. Then maybe I could give it a try. Okay, back to the interface. So let's define a constructor. Now, how would we want to construct a thread pool? I would imagine a good parameter to the thread pool's constructor would be the number of threads, right, that you want it to have. And actually, since we're going to be giving it a number of threads, let's include some standard exceptions in case somebody gives it 0 threads. So std, size t is good because it's unsigned. Let's call it thread count. And we can default it. And what is a good value to default it to? std thread, I think. Hardware, no. There is a hardware concurrency function. Hardware, let me look it up real quick. I think it's part of the thread class. So let's see. Hardware concurrency. It's a static, there we go, okay. So thread hardware concurrency. It's a static member on a thread, and it tells you how many CPUs you have in the system. So let's use that. It's a good default value for a thread pool. So we will default it to thread hardware concurrency. And this computer here has an i7, 4 cores with hyperthreading, so 8 logical cores. We will see that. And let's make this constructor explicit, so that for some reason, if you pass a thread pool as a argument to a function by value or by const reference, it will not use this user-defined conversion. So if you accidentally then call it with number 3, right? If this constructor wasn't explicit, it would then say, oh, I can take 3 and convert it to a thread pool because of this single parameter constructor. So by marking it explicit, you're preventing that from happening. And we will definitely have a non-trivial destructor of the thread pool. So let's declare that here. And why would we have a non-trivial destructor? Because thread pool may be going away, your program may be exiting, but there may still be things on the thread pool that are queued up. So you may want to either kill the execution of those things and shut down those threads cleanly, or maybe try to wait until everything is completed, while at the same time maybe not accept any more items to be queued. So let's think about members. What will this thread will require as member variables? So we know it will definitely need a queue. We'll use a queue here. So std queue, but queue of what, right? We need to answer that. So let's grab functional, and in fact, let's grab memory as well. So what is it that we want to push on the threads queue? So it would be nice if we could do thread pool that do work maybe, and you would give it a lambda, right? No arguments, because thread pool would then just call it without any arguments. But maybe it would have some capture. You would most likely want capture by value, not by reference, when pushing things onto a thread pool, because it's too easy to make a dangling reference error. So when you're enqueuing work on a thread pool using a lambda, make sure that lambda makes a copy of everything it needs. But yeah, it would be nice if we can just do work and do some work on it. Let's say doing work. There. That'll be a nice interface. So in order to define this, let's say work item T is, so our work item that we're going to be putting on a thread pool is std function, which returns nothing and takes nothing as argument. There. And we will be void do work, and this do work will take work item T. Work item. So one other thing I would like to declare is instead of pushing this work item by making a copy of it here, and then putting on a queue with another copy, taking it off the queue, another copy. Let's wrap it inside a unique pointer. So let's see. std so using work item pointer type is std unique pointer to work item, and that is what we will be pushing on the queue. So let's now using work queue type will be an std queue filled with work item pointers. And it's also going to be beneficial that these are pointers, because if we want to cleanly stop a thread, all threads in the thread pool, one way to do it is to push something called a Sentinel on a queue. And Sentinel is a special value that tells the thread, hey, instead of actually pulling it off and executing it, this special value tells you that you should exit. And a good special value is a null pointer. And you'll see how that comes into play later when we are cleanly shutting down all the threads on the thread pool. Okay, so we said work queue type queue. We will certainly need a mutex to protect this queue. Let's call it QLock. And we will certainly need a condition variable to play along with this mutex. So condition variable, let's just call it QLock. And let's just call it condition. And one other thing, Boolean, we will use this Boolean to guard against spurious wakeup. So let's call it check. So it will be false by default. All right. So that's good. Now let's start creating threads. So given the thread count, let's do for auto I 0, I less than thread count plus I. But first, I mentioned we'll be including standard exceptions, so let's do some sanity check. If thread count or just bang thread count, throw std invalid argument, seems like a good exception. Bad thread count must be non-zero. There. So let's start creating threads. Well, but where do we create those threads? You cannot just say create a thread and then maybe, I don't know, detach, right? So we need to have a collection of these threads somewhere. To do that, we can use vector. Things are tricky when you're using collections of unique pointers, but I'll show you why. So let's have a vector. Let's define as the final type def, let's say using threads type equals std vector of std thread. There. Let's t m threads. There. So now we have a collection of all threads, and you'll see why this is helpful. I can tell you right now why this is helpful, because in a destructor, eventually, we will need to iterate over this collection of threads. So let's do that right now. For auto, and here you want to take a reference. Thread in threads, and what do you want to do? You want to join the thread. So you want to wait for it to exit cleanly. Okay. Let's start creating those threads. So threads, and here we don't want to do a pushback. Or maybe we can do a pushback. If pushback can take, okay, pushback can take an R value reference. So that means it won't copy it, we'll move it. And thread, I think, is movable. If not, we will just be pushing unique pointers to threads. But let's try this. So pushback, std thread. Okay, so we're going to be pushing back a thread onto this collection of threads. And this thread will certainly need to capture this, right? So this capture in a lambda, and I think actually it used to be something like reference and dereference to capture a reference to this, or it was something like this. I'm not sure. I think it's C++ 17 or 20. I don't really know. They changed it so that you just in a capture of the lambda part, you just say this, and it figures it out. Okay. So this is our thread. And again, this is Xcode being super annoying with the indentations. So let's see, let's close these parentheses in the right places. Okay. So here is a thread. For now, let's just ask it to sleep for a second. sleep 4. 1 second. So we can then compile it and see if this works. And of course, in order to do that, I have to include Chrono. We will eventually get rid of these weights, but as we're developing it, they may come in handy. So remove me. And in order to do this, I need to use std chrono or chrono literals. These chrono literals are those operators that help me write 1 second like this instead of having to do std chrono seconds 1. Right? If I include the namespace with these literals, then I can just write this using namespace chrono literals. There we go. So we have this thread. Let's put some tracing. So std cout. Maybe let's print out the thread ID. Thread this thread. Let's see. Get ID. No. See, I have to go back to the documentation. I'm sorry. Std thread, not thread. I'll find it. And how do I get ID? Okay, public member function, non-static. All right. Or represents the ID of the thread, public member. This thread get ID. Thread starting. There. Unexpected namespace name this thread. Unexpected. Come on. It's not a namespace. It was a static class. Well, back to documentation we go. There was something called this thread. I guess I forgot where it actually is. This thread. Come on. Yes, yeah, std. This thread. Just need a thread. There. Chronos, they're doing the same thing I'm trying to do here. std this thread. Sleep 4. Why is it not liking it? std this thread. Expected expression. I just want its ID. Come on. Build. Maybe that's just IntelliSense being silly. Nope. Unexpected namespace. What? Oh, this thread. Okay. I think the way we can do it is maybe like that. Let's see this one. Nope. No. Again, back to the documentation. Thread. Come on, load. Load. I just want to be able to print out its ID. Let's see, it returns the ID of the thread, not native handle, just the ID. Yeah, thread, ID, T2, get ID. So why can't we do it on this thread when this thread, sleep 4, works? Okay, fine. It wants to be difficult. We'll get back to it. So this thread starting, std, cout. Let's call it pool thread starting, pool thread stopping. And here in the destructor. We're going to wait for all of them to stop. So good. Let's maybe trace some more. std, cout, creating thread count, pull threads. So we can see exactly what's going on. Here, do work. Okay, that does nothing for now. It's fine. That should build. No problemo. Let me actually try to this thread. I get ID there. See if this will work. So this thread, main thread ID. Let's see, it likes this. Yes, it likes this. Okay, let's do the same thing in the threads we're starting. So thread pool std, this thread get ID starting. Okay, very nice. And thread pool thread std, this thread get ID stopping. Okay. Happy now, compiler? There we are. All right, so let's run it, see what happens. Creating 8 pool threads, pull thread, thread pull. Yeah, see, none of it is synchronized, so it is printing all over itself. That's fine. We can solve this real quick by doing std, maybe something like cout lock. So let's lock inside this thread. std unique lock. There, unique lock. We'll call it cout guard. Let's lock cout lock. We'll get rid of it soon. I just want to have it here so you can see nicely synchronized output. There. Full thread, starting, stopping. There we are. See, it was starting and stopping one at a time because they were taking this lock, right? So the entire duration of the thread was prevented any other thread from starting. Let's see. Okay, so this looks good. Okay, now let's get rid of that. So the thread is starting 8 threads. Okay, starting, then the exit. Let's get rid of this. In fact, let's get rid of everything. Right, so let's start with the do work. So as I mentioned, in order to do work, we need to std, we need lock, we need to acquire a lock on the queue first. Guard m, let's actually rename it to QLock, so we know exactly. QLock, there we go. So let's protect the queue. But before we do that, let's create work item, and we said that work items are what? Work item pointer, yeah, they're unique pointers. Let's see, work queue, okay. Work item, and work item is this function. Okay, so work item equals std, make unique, and we will be making a work item t. Let's see. copy constructed, or let's just std move the one that came in, into this. Let's see, in order to use std move, I think I need utility. It's likely included by some of the other headers, but I like to include them anyway, just to make sure that if I ever change some other part of code, remove some other includes, then that this won't suddenly start failing. Okay, so we created a work item by creating a new unique pointer of this type, moving, we moved whatever was passed to us into this pointer. So now that we have a lock, let's see, Q, I don't exactly remember the interface, but I think push is a good function to call. And again, because this is a unique pointer, we need to move it. So move work item. There. This should compile. Let's see. Good. That's built. And then one last thing that we need to do now that we have this lock on the queue. I mentioned spurious wakeup. So let's now set this mCheck to true. And what this mCheck will be used for in a bit is to tell the condition variable. Condition variable, its wait function has two signatures. One is it just waits on the mutex or the lock. Yeah, it waits on a unique lock to the mutex. Let's see. And the second wait function can accept a predicate. Okay, and this purpose of this predicate is to check and repeat the waiting while this predicate is false. And this guards, see, this overload may be used to ignore spurious wakeups while waiting for a specific condition to become true. So that's why I put this check boolean here. So we are going to set this check, and then finally, what did we call this variable? Condition notify one. Notify one because there maybe there will be more than one thread waiting, but we only want to wake up one. So this will wake it up. And actually, let's narrow down the scope of this locking. So let's do this. So this will take the lock, move the work item we created onto the queue, set this flag, and then when we call notify one, this QLock will already be unlocked. It's good to do this. If you have a function that needs to take a lock, access some data structure, and then do a whole lot more stuff, don't just do it at the top of the function. Put it in its own scope, subscope, so that you're only holding the lock for the absolute minimum amount of time that you need the lock. If you can release the lock and then have the function finish the other 90% of its work, then do that instead of holding the lock while you're doing work. That's at that point unrelated to this lock that is protecting some resource. So that's why a good practice, in my opinion, is to create those subscopes. Okay, so do work. So let's put some work items, and here we'll create mutex to guard. See out guard, and inside this do work we will first take a reference to this guard. Oops. And before we do any work, which in this case we're just printing stuff. We will do unique lock guard cout guard, right? And this is an RAII object. This unique lock is a local stack object, takes a reference to a mutex, locks it in its constructor, unlocks it in its destruct upon exiting set function scope. Okay, let's just move this up. Yeah, and our thread. Yeah, starting. Let's push some. Let's see. We had how many? We had 8 threads. Let's do this in a little. Or I 0. Let's say we are going to give it let's start with 25 work items. So we will take this. Cout guard by reference, but I want to take this I by value, right? I cannot take a reference to this variable here. That just lives in the scope of this loop. So that I need to copy. And I can say that I'm taking the cout guard by reference, but the count, so I equal I. Well, looks kind of weird, but that's how you can tell it. Hey, make a copy of this I variable and call it the same thing. So now when I refer to work, when I refer to I here, when I do this I, it no longer refers to this variable. It's declared here in this loop. It now refers to its own copy of it. And that's the syntax. Maybe I suppose more intuitive would be to say copy of I, and then just use copy of I. But anyways. All right, so we have that. We have this guard. So let's see if that is going to work. Good. It succeeded. That's still good. Now, of course, nothing's going to happen right now. So now let's go work on the actual thread pool worker threads. Let's see if we have, because I believe everything else may already be good in building this basic thread pool. So let's look this over. We have a constructor that's going to wait on all the threads to finish. Good. To work. Good. Okay. There's something else we need in the constructor, and that is we need to push that Sentinel, right? So we're creating work item with a fresh new unique pointer. We moved that onto the queue. So let's signal to the threads that, and again, let's do it in a subscope. As I hear somebody in the background. Is somebody trying to ask a question, or is somebody not muted?
Yeah, not muted.
Not muted? Okay.
Yeah. Yeah. Sorry.
Guard. Let's guard this QLock. And let's now push Q push. Let's just let's see, where's the work item? Work item pointer. Let's move that there so I can actually see it. Well, let's see. So yeah, actually do it. So let's construct an empty work item pointer. Let's see if this will work. it's constructed in place here. Yep. So it's an R value. So it's effectively creating this this unique pointer, moving it onto this queue. And this unique pointer obviously points to nothing, but let's be explicit about it. Okay, so I didn't need this work item pointer earlier, so let's put it back where it was. Let's keep those aliases private. If they don't need to be public, then they shouldn't be. Right, work item. No matching member function to call to push. Work item pointer. What did I do? Work item pointer. Is it because of the snow pointer? No. What does it look like? It just worked. Come on, Xcode. Show me the errors. No matching member function called push. What are you talking about? Doing this on MQ. Oh.
Is it pushback?
Right. No, it's not. It's that the work queue type def that uses work item pointer was declared before declaring work item pointer. So as far as the compiler was concerned, this is a completely unknown type to it. There we go. Okay. So we are going to push a Sentinel. And I'll show you why I'm only pushing one instead of n. It'll be a pretty neat trick. And finally, let's say m condition notify one. Let's just tell at least one thread that, hey, you're ready to exit. And then let's start. So we're telling one thread that it's ready to exit by pushing the Sentinel on a queue. But in fact, all of them will exit, and you'll see how. And again, right, I want to do this. Here I have to do it in a subscope, right? Because if I just took this lock for the entire duration of the destructor, I would be holding this lock and then telling the threads, okay, now go finish. But in order for the threads to finish, they have to be able to take this lock and actually pull this Sentinel off the queue. So it would be a nasty deadlock if this wasn't in its own block. Here, it likely doesn't matter so much. It's just an optimization, I suppose. But in this case, if I remove the scope, we would have a deadlock right away. Okay, and we pushed 25 work items, doing work. All right, creating thread pool. It's so many threads, that's fine. Okay, so now that we're in the actual thread, inside a thread pool, we want to start processing those work items that are coming in. So, and we want to do this in a loop, right, indefinitely until we're told to stop. So an infinite loop seems like a good thing to start. Well, true. And what do we want to do now? Let's see. First, let's create a work item pointer key. Let's call it work. Keep it empty for now. But just let me get back here real quick to the structure. See if I can initialize it with a new pointer to be more explicit. Yes, good. Let's do the same thing here. Okay, so this is just a work item that will represent the work that I am asked to do. By I mean this thread, this particular thread in the pool of threads. Let's open scope again, and in this scope, we are going to unique. So we need to try to take this QLock first. Let's take unique lock, call it guard m QLock. Okay, so we need to have this locked before we can enter into a condition variable's wait. So we have this, Now, mCondition wait. See, and it expects a unique lock as a parameter, or a unique lock as a parameter and a predicate. So this condition that wait on a guard means two things. Hey, unlock this lock first, and then wait to be notified. And when you are notified, then, as I mentioned earlier, it will atomically signal the condition variable and acquire the lock. And how to deal with a spurious wake-up. You add a predicate that, let's see, this predicate needs to take this again, because it needs to check this mCheck variable, right? So while, and then it's supposed to return a true or false, but not in here. Yeah. So let's just return mCheck. And currently mCheck is false. So if the condition variable wakes up, in order to check whether it woke up due to spurious wake up or not, it will look at this mCheck variable. And it will only be true if we have actually pushed something on a queue, right? Because we set it, this mCheck here. So if it's false, then the condition variable knows that, it was a spurious wake up, let me go right back to sleep. And in this thread pool, this check and this queue can only be accessed by one thread at a time, right? So because we release this lock here, then some thread will wake up, acquire this lock, then release it by waiting, and then again check this. So now, first thing we can do, since we are now going past this wait statement, because this predicate gets called internally by the condition variable. So now that we know that we have unblocked, we can immediately reset it back to false. And then we need to acquire the work that was put on a queue for us to do. So let's see, back to documentation. Which is so embarrassing. Let's see std. Because I believe you cannot just pop things off a queue. You can examine the top, there, see? Back, front, push back, pop front, right? So front just returns a reference to what's at the front of the queue. And once you acquire it, only then you must call pop front. And that is, it's by design this way. Because I believe that's the only way that Q can provide strong exception guarantee. Because if you try to do pop front, if pop front returned an item that was at the front of the queue and at the same time removed it, the process of copying it out or moving it out of the queue, that could throw an exception. And strong exception guarantee means that, hey, if there's an exception thrown, I am in the same state I was prior to making this call. So there is no way that it could guarantee that. If popping this element off the front of the queue would throw an exception, that means it's possible then putting it back on the front of the queue would also throw an exception. So the queue could get in a state where it can no longer revert its actions. So in order to guarantee that, we have a separate front function that just tells you, here, access the first element, const reference, well, or reference. Okay, good. So we should be able to move out of it. Okay. So front, this returns reference to the first element in the queue. Okay, and then we have a pop. It looks like there's a pop front for some reason. I don't know why that is. Front, back, pop, removes the first element. Okay, we'll just use that. So again, front and pop. Good. So yeah, what did I do? Here, let's do work equals std move. We want to move it because it's a unique pointer, right? We want to move it off this queue. So mq dot front. And I really hope this is going to work. If not, we're going to have to just use raw pointers. And let me see something before I forget. Push work item, da-da-da, da-da-da, work item key. Okay, I think everything looks good. So we moved it off the front of the queue. Oh, that's why I wanted to check push. So push, let's just be sure that push, so it was push and push back, right? So push inserts element at the end. Okay, good. So why did I see this pop back, pop front? I wonder if there's a push back. Maybe not. Okay, back to coding. So push pushes to the back of the queue. Good. Front gives us the front of the queue. And then finally, enqueue that pop. There. So that will pop it off. And we're doing all of this while holding the lock, right? That guards this queue. So this is good. But then, see why you want this scope. Because what if this work takes a long time to execute, right? So you want to do it outside of the scope, because otherwise, why keep a lock to this queue for as long as you're executing this work? That would make no sense. That would prevent all the other threads from actually being able to do anything, because they're waiting on you not just to take the next work item off the queue, but to actually finish your work, which defeats the purpose of a thread pool. Okay, so now that we have it, let's we know it's a pointer to this function. All right, so let's dereference it, work, and then it's a lambda, it's a callable. Let's just call it. So, bam, that's it. That will just do the work. However, I mentioned earlier the Sentinel situation. So how to cleanly exit the threads. So we have to check for the Sentinel, right? We cannot just dereference this and then hope everything works, because at some point it's going to dereference a null pointer. And in fact, let's run it and see that that happens, in fact. And you should see, when we run it, you should first see it print out that it's doing this much work. Let's just give it 5 for now, so the output isn't too cluttered. And it should do main work. And now what? Got stuck. It pulls thread, thread ID, da-da-da. It got stuck. I wonder why. Let's look at the threads. All right, the main thread is, yes, trying to join. That's fine. And then all the other threads, let's see, thread 2 is waiting for a condition variable. Okay. Thread forward. Thread 3 should be doing the same. Not actually doing any work. Thread 4, 5. You know what? Let's try something else. Let's put a breakpoint inside the work item. So do work. Come on, Xcode. Deadlock. See out. And I wonder if a mutex in a single condition variable is in fact enough to make this work. But I think it is. All right. So breakpoint here in the worker. Try it again. See what happens. Okay, well, here we are. So it created 8 new threads. What is our call stack? I suppose it's this. Function, thread pool. Yeah, so it's coming from here, right? Going through all this. I don't know what to call it. So let's just call it call stack. Okay, now it's trying to acquire this lock. Good, so 1. There's another thread trying to do the same. 0, 1, 2, and then they get stuck. This time it got to do it 3 times. All right. Let's see what's going on. Maybe it has something to do with this check variable being synchronized or not. The fact that it's bool, but it shouldn't. Because those weights are full memory barriers, so that means all the caches or the values should be synchronized across threads. But anyway, let's go back to this and check for the Sentinel. So first, if we got a Sentinel, so how do we check for that? So we can do bang work. That's an operator overloaded for unique pointer. So if work is null, well, we definitely want to break out of the loop, right? But we only pushed 1 Sentinel here. So then what? Well, first of all, we need to move it inside this this scope, I think. So if work is null, then let's just turn around and push another one just like it. So this way, let's see, this way the next thread will be able to do the same thing. The next thread will wake up, pull it off, see, okay, it's null, and this process repeats until all the threads exit. And I believe here, actually, no, let's put this in its own member function. It should be cleaner this way. And then we can call this member function from the constructor. So let's add a function. We call it stop. This will stop the thread pool. And what do we want to do in this function? We want to take this lock, right? Do all those 3 things. So we want to take the lock. We want to push an item on a queue, but not work item. We want to push a Sentinel. So that would be this. Let's see. Queue. Yeah. Push a Sentinel. Set the value check to true and notify. Condition that notify 1. Notify 1 is sufficient. I need to wake up all the threads. Okay, so we have a stop, and we can call this stop from the constructor. Okay. So we should stop the thread. All right, let's see. Ta-da-da. We don't need to call this here explicitly because we have, right? So we have a stopping mechanism. Okay. So now, let's get back to this scope we were in. Why is it complaining? Pointer. Well, it's probably IntelliSense. I don't know. Let's see. Okay. Yeah, I see why. One too many curlies. So if work was null, then instead of doing this, I think we should just call stop. Alternatively, this stop function could, I suppose, push as many sentinels on a queue as there are threads, and maybe notify all. Maybe not. I'm not sure. Well, let's see if this works. Okay, so if we have, if we got a null, we're going to stop it, and we're going to break out of this function. Otherwise, we are going to do our work.
So what if we do not pop back if the front, whatever the element we checked at the front was Sentinel, then we just do not pop that there. In that
Then the
condition.
next thread, yeah, then the thread pool would just keep doing the same work item over and over and over, and never moving on to the next, right? Because all the threads would take a lock, wait to be notified, move it off. And
no, only
well,
in
actually,
the
no, the
condition
next thread.
If work was null.
If work was null, then okay, say again.
If work is null, then do not pop, otherwise pop. So we will not have to push as many sentinels as, the number of threads. Only one sentinel will work the same.
Right. I see your point. Yeah, I suppose that could work. Yeah, or we could examine it here after taking it, right? Take it off the queue, and if it is null, just like you said, do not pop it off, just break out of this loop. But we would still, I think, have to notify the next thread to start fetching something off the queue. Let's see, maybe we can try this later. Let's see if this will now work. Okay, breakpoint and stop. Okay, let's put maybe not put a breakpoint here. Let's see. See if this still goes. Succeeded. Good. Run. What's gonna happen? Okay, so now we got one. Do we work two? Now we got a call to stop from where? Okay, from the main function exiting. I see. So stop. That's fine. So that should keep the and it looks like it's stuck. Doing work 0, 1, 2, 3. Should have done work 4. Why? Let's pause it. So there is a thread here we didn't join. Okay. I suspect maybe it has something to do with the fact that we're doing it outside of the main function. So in fact, let's put this we can put this in the stop function, or no. Apologies, but we're gonna go back to the way it was before. We're going to remove the stop function. Put it back here. Actually, never mind. Let's just stick with it for now. But let's call it explicitly. So here, thread pull that stop. So it's being called before main thread exits. That may or may not have something to do with this hangup. I'm not sure. Let's see. Okay, and then so stop just does that. Notify one. And let's actually make stop also wait on the threads. So we will put this locking, pushing, checking, and notifying in its own scope. And then we will wait on all the threads. And here we can actually, let's add another flag, pull m stopped. So if we call stop again from the extractor, we're not going to be doing this twice. So let's see, let's try to take this lock. And if the thread pull has already been stopped, so if stopped. Let's return. Otherwise, set check to true, set stopped also to true. There. And then notify one. Because notify one wakes up one thread that's waiting. But what if at a given time, no threads are waiting because they're busy actually doing work? I wonder if this notify one gets lost in the ether. It may. Let's see what the spec says. Variable wait. Okay. So notify one notifies one waiting thread. Okay. Unblocks one of the waiting threads. Right. What if there's no thread waiting? Let's see this. Okay, so I think here it says that this makes it impossible for notify one to, for example, be delayed and unblock a thread that started waiting just after the call to notify one was made. Okay. Well, let's see, that would be a problem. So let's change something here. Let's see, in the do work, we notified after releasing the lock. Good. So here on stop, we should probably do the same thing. We should release this lock first. See if we are stopped. I'm going to return. Otherwise, we're going to push a Sentinel, mark the check, and mark stopped. Release the lock and then notify a thread. And then wait for them to. Good. And we should probably do the same in the worker thread. So let's see. So not stop. Yeah, we don't want to call stop here because it waits for all the threads. So the thread would wait on itself to exit, which, if logic serves me right, would never happen. All right, 1 second. So let's see. So now, if the thread was stopped, or if we got a null here, so we have already unlocked this. All right. So instead of calling stop, I think we can just notify another one. But where would we push the Sentinel? Let's see. So here we got work. Okay, we popped it off. So let's do this check here as well. So let's see. If work, this is the last one, right? So let's push a Sentinel here. So MQ push, and then what do we call it? Work item pointer there. Type. Right, so we are pushing it on this queue while we're still holding a lock to it. Then we're going to exit the scope. And if it was null, then we're just going to signal this condition again. Notify one. Hoping that somebody's there waiting on it. Because the problem may be, and I'm not sure, if you notify one, right, but there isn't a thread waiting on it, I think we just read that. And then that would not wake that thread up. We'll see. All right, let's see how this works. Run. Well, it's stuck again. Let's retry it. So if we get a different let's see, I'm able to do 3. Let's look at the work that we're actually doing. Let's try not locking there. See what happens. Still get stuck. Doing work 1, 2, 3. Okay. So we have a deadlock. So let's see if we can try to find it. Oh, look, now we did 4 work items. Yeah, I suspect it has to do with the fact that we notified. Let's change this notify 1 to notify the, maybe that's the way to fix these. So when we are exiting, maybe nope, still a deadlock. Run it again. Sometimes it gets, now it only did 2. Okay, interesting. I am pretty sure we shouldn't be calling notified all in this, but let's see what happens. Oh, the order changed. It's interesting. And let's see what those threads are doing now. Da, 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 da. Yep, this one's waiting. Another one, thread 9, waiting on condition variable, like we expected. Where's the start of this thread? There, yeah, it's waiting. Next, doing the same thing. Okay, so they're all waiting. Yep. Another one waiting. And another one waiting. And another one waiting. Okay. On the condition variable. Let's see. Maybe. Let's try to do this pushing of sentinels and shutting down threads in a loop slightly differently. So let's see if we rework this to do for thread in m threads. Let's see, so for all the threads, let's push that many, notify 1, and then wait on them. Let's see if this will make a this will make a difference. See, when I built a thread pool before, I actually didn't use condition variables to synchronize the worker threads terminating. No, that's different. Sig abort. How did that happen? Thread pool. This was the constructor. Probably that's right. There. Let's see. Let's take the lock on this too before we before we check it. As I was saying, I have a thread pool implemented here, but the way I did it was I used a blocking queue, so the threads never really needed to notify one another. There, okay, so doing work. All right, so now it did. So now it did all the work at least. So let's pause it, and those threads are still there. They're still waiting. Well, there's less of them, right? So something here helped. Let's see. Let's put some tracing back in the thread itself. So here, creating spinning wheels. Let's see. Let's put this cout guard back up top, so we can synchronize the printouts from the worker thread starting and stopping. Here, all right, so when we enter into a worker thread in its own subscope, unique lock, we're going to take lock on this cout guard, std, cout, full thread. Let's give it the thread ID. Std, this thread, and then see how do we do it before. Was it dot get ID? I think it was. Yeah. Oh no, this thread call get ID. Okay, get ID. Starting. All right. Let's put the same thing at the end. Stopping. Let's see where that takes us. We should see all of them starting. So we can build. Next is cut. That's right. Because it's a global and a static. Let's actually make it static. Just to be sure, it doesn't need to be captured. The lambda can just access it. So we can change the capture mode to just equals. So we'll just copy the I by that. Okay. So pull thread starting. Okay, they did all the work. And then pull thread stopping. That's good. But not all of them are stopping. How many did we start? Let's see. 1, 2, 3, 4, 5, 6, and 8. Good. It looks like yeah. Let's print this before we create the actual thread. There. Then it's doing work. It's fine. 8 of them starting. It's like they all at least get to complete their work that they're doing. Then we're stopping the thread pool, and that's where we run into a deadlock. So let's see if we can work through this. First, let's see if it will take more work items than there are threads. This should tell us that they're getting to do the work, and as I suspected, they're not. Okay, see, so we're pushing the work on here so so quickly, I suppose, that it unblocks, it calls this notify one every time we add a work item. But at some point, we get to a point that we're doing work 8, yeah, that all the worker threads on a pool are actually busy doing the work. So this notify, has no effect. It has no effect on waking up these worker threads that are stuck here waiting. Huh. Yeah. Let's see. How could we solve this? So we have multiple threads that are busy here doing the actual work. When right, so we could fix this by I think if we remove the scope, I think that should definitely fix it. But that's not how you want to do this. Maybe it will fix it. Yeah, just it helped a bit because we are holding the lock longer, but still not long enough. Suggestions on how to go about this? I wonder if there's something to do with this check, maybe. Let's see.
So when a thread is done with working, are we exiting at that point?
No, we are not, because we are in this loop, right? And then we go loop around again. We start waiting on this condition variable again to see if more work has been queued up. Right? We're only going to exit the thread if a Sentinel got pushed on it. So if we detect that somebody else pushed this null pointer, then we exit, and we do this here. Yeah. So maybe let's change something here. Yeah, I don't know. I don't want to spend too much time debugging through this, because these multi-threading things can take a bit of time. So if I don't figure this out in a bit, I'm just going to call it a class. Let's see. So when we get a Sentinel, we're going to push another one, notify one. I'm not sure if this has effect when we are actually holding holding the lock. Let's see. Yeah, it doesn't. And here, all the threads. All right.
Would it help to remove all the locks to try to see which one is problematic?
No, because without the locks, we cannot use a condition variable, right? Without the locks, we cannot do this wait. Now, let me look at something here on the side, because I have a event class which I was using recently in, was it here? Yes, and this event class I'm pretty sure would fix it, because if I did a automatically resetting event. So instead of doing the condition variable, oh, wait a second. Let's see something here. Where was I taking this by reference over there? I'm not sure. Does this have anything to do with it? Right, this reference will just take this as well. Okay, let's put this back to the way it was. No need for this. Yeah, see, I think I'm pretty sure I can rework it with an event object. But I wonder why. So if I had an event object, it's an auto event. So that means that once it's been signaled, it will then unblock somebody else later who's trying to wait on it. And here, see, I do a similar thing. Take the lock, mark it as signaled, then release the lock and notify one. And the waiting function tries to take the lock and releases it by waiting, has this spurious wakeup predicate, so while not signaled, right? So that means, maybe I have this predicate wrong. If signaled is not equal to false. So if signaled is equal to true, then it will return true, right? And then this. So am I doing something different here in this event that I know works versus here? So let's see. So adding a work item is kind of like signaling, right? So let's look at this. So adding a work item to work. We make something. We take the lock, just like an event. Yeah, we take the lock. We push something on the queue. And then we say check, which tells it that I did in fact push something on the queue. Just like this thing. And then the wait, right? Unique lock, wait. Check for this. So then the wait in this thread is unique lock, right? Wait guard for check not equal to false. I don't think it matters. This is logically equivalent. Check not equal to false, right? And then here immediately, once it was waited and it stopped, the signaled or the checked is reset back to false. And the signal is a regular Boolean. And then a manual event, which means it's an event that does not reset until you call a reset on it. Take the lock, you signal it, notify all, and the waiting thread first takes the lock, sees, right, was it signaled already? In this case, at this point, it can block. I wonder if that's, oh, okay. I think I know what this may be. I think this gave me a clue. So here we take the lock first, and then we check if it was signaled. If it was, we just return, right? So let's do the same thing in the thread pool. So if Yeah, I think this may actually work. Let's see. Let's fix these indentations. Let's look at the do work is fine. Stop. Yep, stop is fine, I think, since it was already stopped. Okay, here let me clock, push, check, stopped, notify one in a loop. I think it's fine. Okay, do work. That's irrelevant. So I think the mistake here may be that once I acquire this lock, I am already ready to check, right? So I don't need to acquire this lock and then release this lock and wait on this to be checked. Because what happens is that another thread is pushing a work item, right? So it successfully gets the lock, it pushes a work item, and then notifies one thread. However, there's no thread waiting because they're busy doing something else. So maybe here, if I try to acquire this lock, first thing I should do is if check is equal to false, right? So if nothing was put, well, then we wait. There. Then we are going to wait on a condition variable until we are signaled and it is set to true. And at which point, just like this event, we will unblock on this wait in the automatic event, right? The wait will unblock. We will switch the state of the signal parameter value. We'll get our thing, pop it, and then release the lock. So the change here is to wait, conditionally wait only when we know that nobody actually pushed any work on the queue. And also, I'm not sure if check being a Boolean is enough. If it's not, we can change it to a size t, and it's going to be counting. So every time you add something to the queue, we will increase it. And every time you remove something from the queue, we will decrease it, its count. And we will only wait if the count of elements on the queue is 0. Good. Let's see if this simple change works. If this conditional waiting will fix our deadlock. No, doing work. Let's see how many works did we do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we did more work than there are threads and cores, but looks like that was not enough. So let's do this counter idea. So instead of calling it check, let's call it count. std size t. So we will do count. And this count will be the current number of items on the queue. So when we are pushing something on a queue, like the Sentinel, we are going to ++ count, so increase it, right? Let's see, this is fine. Modify 1, join, yup. And then do work here again when we are pushing something on the queue. We will increase it and check or no count. Right. Now we're going to release and notify somebody. So if there's somebody waiting, right, at least one thread will be woken up. But if there's nobody waiting because they're busy doing work, then they will loop around here and eventually get the lock, see if there is actually something on a queue. So this is m count. And if there is nothing on a queue, then because we're still holding the lock, nobody else can signal us at the same time. So this do work thread will block here before it's able to call notify one. So let's see. If this doesn't fix it, then I don't know what will. So m count. Right? And if we do decide to wait, when we unblock from the wait, right, that means we have reacquired the lock. We can then decrement the count of elements in the queue. Yes. All right, let's try it. So check false not equal false. So this time it will be m count is greater than 0. Okay, that is the condition which indicates that we can actually wake up. Now I am wondering about this. Do I actually need it now? This repushing and re-notifying, because the stop function now will push as many as there are threads. We'll take a log, push the Sentinel, increase the count. This stops true. That's just so that if it gets called from the distractor of some other thread, it's not going to try to stop it again and go to this dance here. Right, so it will push the Sentinel, increase the count, and notify one. And then wait for all of them to exit. And if this notify one has no effect because nobody is actually waiting at that time, that's fine, because we increase the count. And because we increase the count, when this worker thread loops around, fires the lock, looks at the count, and says, okay, if there's something there, I'm not even going to bother waiting, right? No point in waiting because I know there is work there available. So let me take it off the queue. And we can actually most likely remove this whole counting and probably replace it with just checking if the queue is empty or not, since we already have a lock. So maybe we'll clean this up, but let's see if this will actually work. If I want everywhere, start, stop, okay. If it doesn't work, then I am completely embarrassed. Let's see. Run. Look at that. It ran and it exited. Thread starting, then threads are stopping.
Yeah, exit code is 0.
Yeah, the exit code doesn't really mean anything here in this case, but
yep.
The point is that it did work number 24. So it did the last work item, right?
Right. It's a normal exit.
It's what?
It's a normal exit. It's a successful case.
I really cannot make out what you're saying. It's breaking up a bit.
Okay, so I was saying that it seems to be completely successful, that it did all the work and exited normally.
Right. Yeah, that's right. Let's see. Let's try it again without this tracing so we can actually count. Yeah, this looks like 25 lines to me.
Right, yeah.
Yeah. Okay. So let's clean this up now. We don't need this tracing here now. Yeah. So you see what my mistake was, right? My mistake was waiting on the condition variable regardless of there being something on a queue or not, right? Once I acquired a lock, why would I then immediately go back to releasing it and waiting, right? It only made sense if there was nothing on a queue. Once I have the lock, that means I'm ready to do work. And if I'm ready to do work, that means it's a mistake of me to go back to waiting, because this condition variable may have already been between me getting this lock, or yeah, before me getting this lock, the condition variable could have been signaled. So by the time I get here to this wait, I will never receive that signal, right? Because we read there in the spec that this makes it impossible for notify 1 to, for example, be delayed and unblock a thread that started waiting just after the call to notify 1, right? So that was the mistake. Yeah. So now let's see if we can clean this up further. Threads, so we don't need this anymore. And instead of the count, let's see, let's move this cout guard back to the main function. What do we get? Here. No need for it to be static anymore. Good. Thread pull. Now we need to check it by reference again. Yeah, so globals, statics, they don't require capture into the lambda. They're just visible automatically. Okay. Let's see, stopped. I wonder if we need stopped as well. So in fact, let's move all the stopping back into the structure. Use that, and see if we can get rid of the counter. Because the counter really, it just answers a true or false question, whether the queue is empty or not. We don't really need a count, we just need to know whether it's empty. Okay, so do work, that's fine, no need to count here. Stop, let's put all this work back in the constructor. So on a stop, we want to, let's rewrite this again. std, unique lock. We want to go, let's see, QLock. Yeah, we want to take the lock on a queue, and then for as many threads as we have, and queue, push that Sentinel. So we push as many as there are threads. This way, the thread, when it's exiting, doesn't have to push one back, right? I told you there could have been the trick where I only push one Sentinel, and then the thread, when it detects that there's no work, right, it pushes one back. But in this case, it doesn't need to do any of that. Just checks if it's null, exit. That means we're being stopped at this point. Okay, so in the where's the structure? Here, in the structure, acquire the lock, push the sentinels on, and then finally we can just wait on those threads here, and we can get rid of the stop method. Cleaner interface. So basically, the thread pool lives for as long as instance of it lives. We don't need to do that. Count. Let's be brave and get rid of it. Up to the top. Count. So instead of count, we are going to say mq dot empty. So if the queue is empty, here then we will go to sleep. And there is no way we will miss the next notify one call to the condition variable, because nobody else can do it since we're holding this lock. And we want to check for spurious wake up, and our check for spurious wake up is have this predicate return true when there's actually something on the queue. So let's, from here we can call bang m q empty. So if it's not empty, then we're good to go. I'm gonna wake up, reacquire the lock, get the next work item, pop it off the queue. We can then immediately release the lock. And then if the work we were given is no work at all, break out of this thread. Otherwise, do the work. There, so we cleaned it up. Let's see. Actually, let's run it, let's give it 50 and run it from the console. See, I'm doing a debug build, so if I go here, okay, into Xcode, into bin, into debug. Oof. So remove all these executables. Let's just rebuild this one. Again, go there, playground. Stretch this guy out a bit. Playground. Here we go. Main thread ID, and then doing work 50. Interesting. They're all doing work 50. What is? Okay, right. They're doing work 50 because I'm taking I by reference. Right. So this call to deleted function var. Okay. So I have to take the cout guard by reference, but I have to copy into the function, right? Because if I'm just taking the reference to I, so by the time I get to print this out, this loop has finished, right? And I is 50. That's why it was printing, doing work 50, which almost gave me a heart attack. But luckily, there. So here's your thread pool. You can push. Now, there are better implementations of this as far as performance is concerned. And I have one. I've implemented one in the past based on a talk by Sean Penn, I think his name is. He is he's one of the top engineers at Adobe.
Yes.
He talks about
Sean Gather you're talking about.
Mm-hmm. Yeah, so I have an implementation of that pool as well. So this is this simple thread pool. This is sort of what I went through today, plus some improvements related to pushing items on the thread, on a queues, and actually getting back a feature object, so you can then wait for something to finish executing on the thread pool. Yeah, and then this is the implementation of the pool that Sean talked about, and this involves stealing from other queues. This one has more than one queue. It has multiple queues, and it steals. If a given thread finds itself not having anything to do, it will then try to go through all the other queues of all the other threads, see if it can take something of those queues without actually locking anything. That's why it's doing these try pushes on pushing, and then on popping the actual worker thread. It does try pop. It does it in a loop to iterate over the collection of threads several times. And if it can't pop off of it, then it will eventually block on the pop call. Yeah, so this one, especially for short tasks, microseconds, nanosecond, whatever, shorter, millisecond, this one has a significant performance boost. But purpose of today's exercise was to apply some multi-threading concepts in real life practical functions, code development at work. So yeah, does the mistake that I made make sense? what the mistake was and why I fixed it, the way I fixed it, right? We were going back into a wait state after the condition variable was signaled, and then there was no way to yeah, there's no way to detect that it was signaled in the past. So the notify one will only wake up a thread if there is a thread actually waiting on that condition variable, right? If there's not, then it will have no effect, and that's why we were getting into this deadlock, because we should have checked that okay, skew is an empty, and I wonder if now that still would give us. If I just remove this, that will cause a deadlock again.
Yeah, I think both are required.
No,
both check.
I wonder if we're getting lucky. Yeah, I'm not sure. See, if maybe this check is executed once before it's actually going to wait. So maybe if we have this.
I think, yeah, because wherever I have seen conditional variable used, there are two checks. One is in the predicate and one is even before calling the wait, like we have done here in 28 and 29 line.
Mm-hmm. Okay, so you're saying line 28 is needed here?
I think so. I'm not sure.
Mm-hmm. No, because I just removed it and ran it again, and it seemed to have actually worked this time. But that may, I don't know if we are just getting lucky here. Because how would that be different than, I see how that would be different than having the check. We had the Boolean check, and then one thread took something off, I immediately reset it to false, which wasn't the right thing to do. So I don't think we need this here anymore, because the predicate now is better. It's not a check against Boolean; it's check against the size of the queue. So I suspect that going into conditional variable calling wait, probably before releasing this lock, it will probably say, hey, let me check this predicate just in case. And if it already gives you true, then it will just immediately unblock from wait and let you proceed. Let's see if that is the case. Wait with a predicate. So equivalent to, yeah, see there. So the wait with a predicate is equivalent to spinning in a loop and then waiting on a lock. So it does perform the check first, right? It's not a do while, it's a while before the lock, right? So that if statement is no longer needed there because this wait function will inspect the predicate, and only if it returns false will it then release the guard and start waiting. So, okay, good. This is a good start into multi-threading.
Yep.
Does anyone have any questions? Does everything that I went over today make sense? The design, how and why?
Right, yeah. So the do work function need to be uniform. I mean, in this thread pool, all the threads will do the same work, right? Is there any way to kind of have this?
Yes. The behavior of the worker thread is the same for every worker thread, right? Okay. All it needs to do is pop something off the queue, see if it's a Sentinel. If it is, it just exit. Otherwise, it just does the work, right? That's why what you're pushing on a queue, right, is a function with no parameters, no return value, because you don't care about that.
Okay.
So you can, you can push different things, right? Here I'm pushing the same lambda 50 times over, so I'm copying it 50 times and pushing that. But I could push this 10 times. Let's say, let's see, let's put this log guard in here, so it will print, and then it will do we'll do some sleep. So let's first, let's just do this thread, sleep 4, and let's give it some number of milliseconds. So maybe sleep 4, chrono, nanoseconds, stick a random value, cap it at 100. So this effectively simulates these worker threads or these work items doing different things, right? Things that take more or less amount of time. But yeah, I can push 50 of those, or I can push 5 of those, and then repeat this loop with some other lambda here, and it doesn't matter. You can push whatever you want onto this thread pool, right? As long as it conforms to the signature. So it's something callable. I choose lambda because they're the easiest and cleanest to do here. It's something callable, no arguments, no return value, and the thread pool worker threads will just crank through the queue throughout the entire lifetime of the thread. And what you ask it to do doesn't matter. To the thread pool, it's completely irrelevant. It just takes one item at a time and executes it, and then multiplied by the number of threads that you created the thread pool with. So let's see. So this will give it a random sleep value. So now when we run it on a console, it'll actually there. Oh, but I finished way too quickly. On nanoseconds, right?
We can make it milliseconds.
Millisecond. Yeah, that's what I wanted to make it. Yeah, I wanted to wait longer than that. Still, kind of quick. Let's give it a longer random wait. There. And then we're done.